Log on, tune in, find out. Another good idea from Cambridge.
Time bundles on modular stacks of G particles.
Thank you. Good morning. Let me start by thanking the organizers for the invitation to come here and for the opportunity to speak to you, to talk to you. So, what I'll talk about is about principal G bundles, where G over an algebraically closed field K is a reductive algebraic group, connected always, reductive algebraic group. And I will use the center, which I'll denote by ZG. And I'll also choose a maximal torus, which will play some role, T, inside G. And then the G bundles I'll be talking about will all be G bundles over a smooth projective curve. So we also fix for the whole talk one smooth projective curve connected over the same base field. And say genus is not too small. For almost everything I'm going to say genus at least 3 is enough. At one point maybe genus at least 4. And then the main objects that I'm going to talk about are moduli spaces and then later moduli stacks of G bundles on this curve. So let me denote by M, G, S, the coarse moduli scheme, of principal G bundles E, algebraic principal G bundles E over this curve C. Yeah, so that is the main object to begin with. This is not connected. It decomposes into connected components, indexed by the fundamental group. I'll say a few words about that in a minute. By the fundamental group of G. So, in other words, such G bundles have kind of a discrete invariant, a type which is an element in the fundamental group. For example, for G equals GLN, the fundamental group is Z, and this invariant D is the degree. So that's what I have in mind. That's why I denoted D. And if we fix this discrete invariant, then we get irreducible moduli spaces. So these, let me write it the other way around, G, comma, stable. These are irreducible quasi-projective algebraic varieties. Quasi-projective varieties. Okay, so what is the fundamental group here? If we are over the complex numbers, then this is this group G is a complex Lie group, so it is a topological space, and as such it has a fundamental group. And it is actually this fundamental group. But in over other fields, in particular in positive characteristic, this does not so much make sense, but there is an algebraic way to define this fundamental group, which over C gives the same. This is as follows. If you like, you can take this as a definition. It is the co-character lattice of the maximal torus. So that I'll denote by lambda T. This is by definition just the group of homomorphisms from Gm into T. Can everybody still see that T here? Yes, I think so. Okay, so that's a free finitely generated abelian group whose rank is the rank of the torus. And to get the fundamental group, you mod out by the subgroup generated by the co-roots of G. So co-roots of G are elements in here, and if you take the quotient by the subgroup they generate, you get a finitely generated abelian group. That is the fundamental group of G. So So over the complex numbers, this is maybe a small theorem, and in positive characteristic, this is the definition of the fundamental group I'm using here. So this is, in there lives the discrete invariant, the type of such a principal bundle. Now I want to talk about the question of Poincare families, or as they are also called universal families maybe, but there'll be some other universal families, so I prefer this notion here. So what is that? So let's look at some open subvariety. Zariski open subvariety of the moduli space. Then what is a Poincare family, Poincare bundle for this open part? Well, it is a principal G bundle over the product of U with the curve. So it's a principal G bundle. Let me denote it like that. Such a principal G bundle is called a Poincare family, or universal family if you prefer. Poincare bundle. If, by definition, well, if for every point in this part of the moduli space, so this is a moduli space, so its points are at the same time isomorphism classes. So I can view it as a point, small x, and I can also view it as an isomorphism class as of a principal bundle. With every k point of U, I can do that. And the condition is that if I restrict the family to that point, so now I have a principal G bundle over the curve, and the condition for this to be a Poincare or universal family is that this G bundle belongs to the isomorphism class that is given by the fact that we are dealing with a point in the moduli space. Yeah, so it's
So you don't actually assume a universal property for this. You just say it's just the restriction is
yes, that is good enough. I mean, I will anyway only be working the regular stable locus, and there everything is smooth. So I think this will imply then a stronger universal property that you might have in mind. Yes? Yes, it is the topological fundamental group. I mean, this is the topological fundamental group of the torus, because it's Z for each factor, and then you can also check that the map from the topological fundamental group of the torus to the topological fundamental group of G is exactly modding out by the colons. Okay, so this is the object. So this is the question: do such things exist? Yeah? And one of the first main results in this direction is due to Ramanan, 1973. He proved that in the case of vector bundles, such a thing does not exist, no matter how small you make this open part, in the non-coprime case. So if rank and degree are not coprime, and such a thing does not exist for any arbitrarily small non-empty Zariski open part of the moduli space of vector bundles of degree d and rank n. Always Zariski open. Yeah, so that's one of the questions you can ask. Does such a thing exist if you allow yourself to go to smaller and smaller Zariski open parts? The other question you can ask is, what about globally? If I take kind of the biggest reasonable open part, and the biggest part where maybe it is plausible to expect something, or where I can say something, is the so-called regularly stable locus. So this is an open part in the moduli space of stable G bundles, and it is by definition the locus where the automorphism group is minimal. Namely, the locus of those principal bundles whose group scheme of global automorphisms over the curve is the smallest possible, namely the center of G. So the elements of the center of G will always act as automorphisms on any principal bundle, and there is an open locus where there are no other automorphisms, and in fact the automorphism group scheme is not much bigger. These are called regularly stable. For vector bundles it's the same as stable, but stable principal bundles can have extra automorphisms, and these are excluded here now. And somehow, in some sense, this is maybe the biggest open part where you can say, or at least I can say something about this question, and where seems reasonable to ask. And there was, I think, even a bit earlier than Ramanan, there was a result of Newstead, 1973, about the question of existence of Poincare vector bundles, and it was generalized in a paper by Balaji, Biswas, Nagaraj, and Newstead in 2006 to principal bundles. Oh, no, maybe I don't have to. Yeah, okay. So they gave some answer to the question of an existence of Poincare families over this biggest open part, which you might be interested in. It was in the case where the ground field is complex numbers. So the result was, as far as I understand, topological in some sense, and the group is semi-simple. And it's about the topologically trivial component, so the component d equals 0. And the result was that as soon as the center of the group is non-trivial, then there is no such thing, no such Poincare family for the regularly stable locus in the topologically trivial, so for vector bundles in the degree 0 component. So that's what was known about this question. Now I'd like to give a try.
So you said that G semi-simple and then restricted to GLN.
Oh, sorry. No, that is just. Of course, that is for all G. Yeah. And I mentioned GLN as an example. I should have said SLN then. That was your case earlier. So the general answer will be in terms of the root system of G. So let me introduce some terminology, some groups which play a role in order to state the general answer to this question. So we have the group G, and associated to it is reductive. Associated to it are a few semi-simple groups, namely, first of all, the commutator subgroup. That is kind of the largest semi-simple subgroup. Right? And what we also have is the largest semi-simple quotient of the group. We denote it by G bar, so that you can get by modding out the reduced identity component in the center of G. Let me denote it by Z0 of G. And these are isogenous. So that is a central isogeny. In fact, there are two more groups that you can write down, namely the universal cover of this semi-simple group. This is kind of the largest semi-simple group that you can put here with the central isogeny. So we have central isogenies. And on the other hand, there also is the adjoint type group belonging to these semi-simple ones. So that one you get by modding out all of the center. Yeah, so these are four isogenous semi-simple groups which somehow encode the combinatorial structure. Yeah? So if the group is semi-simple, these two coincide, and otherwise they kind of say how the reductive group lies inside all these isogenous semi-simple groups. And this can be codified in terms of the root system, right? So all these isogenous semi-simple groups inherit a maximal torus from the maximal torus in G I've chosen in the beginning. And all these maximal tori are then isogenous, and they have corresponding co-character lattices. So we have the co-character lattice of the induced maximal torus in the simply connected group. I'll denote it like that. This is a subgroup of finite index, because this is a central isogeny, in the co-character lattice of the maximal torus in the commutator subgroup. This again will sit in the co-character lattice of the maximal torus of this quotient group, and this again sits inside as a sublattice of finite index. I denote this by the adjoint form of G. This will sit inside the co-character lattice of the induced maximal torus inside there. These are all lattices of sublattices of finite index. The smallest one is the one spanned by the co-roots. So that is spanned by the co-roots. It's just determined by the root system, by the type of the group. And the largest one is, that is the largest lattice on which all roots take integral values. Yeah, so these two somehow are given by the type of the Dinkin diagram, and these two in between tell you something about which group of that type you actually have. So that is the combinatorial structure that you have from the root system of the group. And now the main player for the questions I will talk about is the following. This will be an abelian group of bilinear forms. It's the abelian group of bilinear forms B, bilinear forms on two of the two middle lattices, namely T bar, the co-character lattice of the maximal semi-simple quotient, pairings of this co-character lattice with the co-character lattice of the maximal semi-simple subgroup with values in the integers. So the abelian group of these pairings which satisfy the following conditions. If I restrict them to this smaller lattice, which is given just by the Dinkin diagram, in both variables, then the condition is that this bilinear form is first of all symmetric. So it's a quadratic form. It corresponds to a quadratic form. This quadratic form is even, which means if I plug in any lattice element here and the same one here, then the integer I get is even. And they are also required to be invariant under the action of the Weil group. So these bilinear forms are the ones which in terms of which these questions are going to be answered. And let me just explain a little bit that this is a very explicit object. So first of all, this sits inside as a subgroup of finite index in the group where you replace the group by the universal cover of its commutator subgroup, if you like. Because if you replace G by that one, then all these lattices get replaced by that one. Yeah? So the condition is only, here the condition is only that you have a symmetric even Weil invariant bilinear forms on this smallest lattice, this co-root lattice. And these ones are known very explicitly. These ones are known very explicitly. This group is just the direct sum over the simple factors of G, and one has one canonical generator for each simple factor of G, which is called the basic inner product, and I'll denote it by B, Gi. So if you decompose this simply connected group into simple or almost simple factors, then you have for each factor one canonical generator, which you can look up in tables in Bourbaki, for example, and these just give you that group. And then in order to understand that group, you just have to ask all these basic inner products, are they or are they not still integral on these slightly larger lattices? Yeah? So that's the whole combinatorial game that's going on. And now the answer to the question of Poincare families is the following. So this is joint work with Indranil Biswas, which has just appeared. So there exists such a Poincare family for arbitrarily small open parts in the moduli space, in the component of the moduli space of G bundles, if and only if the following holds. So a certain evaluation map, which I'll write down in a minute, which goes from the group of these bilinear forms to the group of characters of the center. So it will first go to the group of characters on the maximal torus of the commutator subgroup, and then you can restrict to characters of the center of the commutator subgroup. So how does that map go? Or maybe I'll state it. Yeah, maybe I'll state the criterion first. The criterion is simply that this map is surjective. So surjectivity of this explicit map in terms of the root system is equivalent to the existence of such a family over arbitrarily small. And what is this map? Well, it's more or less just evaluation of this bilinear form in the topological type, in D, in the kind of degree variable. So what you do more precisely is you plug in a lift of D. So delta is an element in the co-character lattice of the maximal torus of this maximal semi-simple quotient. And which one do you take? You just take any lift of d bar, an element in the fundamental group of that. So this here is a quotient of G. So it comes with a map from G to it. So this element in the fundamental group, D, which indexes the components, has an image, D bar, in the fundamental group of this quotient. And since it's a fundamental group, it's a quotient of the co-character lattice. So take any lift of this element to the co-character lattice, plug it in here. So this turns these bilinear forms into linear forms on the co-character lattice of this torus T prime. So linear forms on co-characters are characters. So you get a character, then restrict this character to the center of the commutator subgroup. And the composition will not depend on which lift you chose. That's why I denoted just by D and not by delta up here. And the condition is simply whether this map is surjective. And there's also an answer to the other question. There exists a Poincare family for the largest open for the regularly stable locus. Regularly stable locus, if and only if, well, first of all, this has to be satisfied, of course, and then there is a second condition, moreover, the center of the group is a torus. So in general, it will be a group of multiplicative type, so a product of some GMs and some mu r's. And here the condition is that there are no mu r's, the center is just a torus, product of GMs. So this is the criterion, and once again, trying to convince you that this is a bit combinatorial, but very, very checkable. Let me just quickly go through the computation for GLN. For G equals GLN, just to see how you get back Ramanan's result, for example. So here, the topological type is just a number. The fundamental group of GLN is Z, and the element D is the degree. So here, it so happens that the basic inner product, the generator of this slightly larger group, is still integral on these two. Yeah? So these are just multiples of the basic inner product, SLN. And so you just have to evaluate that one under this map and check what you get. And in fact, what you get is, if you lift the degree to the co-character lattice and plug it into this bilinear form, then I should put GLN here maybe. If you plug in this generator, then what you get here is exactly the class of D. So which group is that? G prime, the commutator subgroup, is SLN in this case. So the center of SLN is mu n. So characters on the center is characters on mu n, which is Z mod n. And what you get here, if you plug in the degree here, is exactly the class of D in Z mod n. So this will generate Z mod n if and only if you're in the co-prime case. So this, this gives back the earlier result. And just because these basic inner products and the root systems and so on are very explicitly given for any type, you can perform the same computation for groups of other types. Okay, so now let me go a bit into the proof. So what is used in order to prove these things? Well, in the background, there is the moduli stack. Mg, let this be the moduli stack. stack of G bundles that also decomposes so not just stable, but all G bundles have kind of a degree, a topological type in the fundamental group. And the pieces that you get here are now connected, even irreducible, smooth Artin stacks. These are smooth Artin stacks. And there is an open locus corresponding to regularly stable G bundles. So this is open. That's by definition the locus where the G bundles are stable and automorphisms are only the center. And this moduli stack now has a kind of a classifying map, a forgetful map to the course moduli scheme. So this sends every bundle to its isomorphism class as a point in the moduli space. And precisely because I restricted myself to the locus where the automorphism group is just the center, the fibers here are all isomorphic to the classifying stack of this. So, I mean, the difference between the two is only the fact that here we are also taking into account that these objects have ZG automorphisms, what we have forgotten here, but otherwise this is kind of a fibration. What it's called is it's a gerb. It's a gerb. And people say with band ZG, which, let me repeat, once again just means here in the stack all the objects have ZG automorphism group, and that is still encoded in that. Otherwise this is kind of a locally trivial in a sufficiently fine topology, say the Étale topology, locally trivial fibration. Okay, and whenever you have a gerb, it has an associated class in H2. So just like a principal bundle has an associated class in H1, gerb has an associated class in H2, and this class is precisely the obstruction against sections of that gerb, and sections of that gerb are precisely such Poincare families. So the class of this gerb is the obstruction class against, denoted by psi GD. So that is a class in, say, Étale cohomology, Étale H2 of the regularly stable locus, which is a smooth quasi-projective variety with values in the center of G. That's the obstruction against the existence of such Poincare families. So this ZG is of multiplicative type, so we have here a product of GMs and mu Rs. So this is more or less a tuple of Brouwer classes. The obstruction is a tuple of Brouwer classes. And in fact, what we prove is a little more precise than the theorem I stated above. Actually, what we prove is the following. We compute the order of these obstructions in these Brouwer groups, both generically, so on arbitrary small pieces, and globally on the whole regularly stable locus. And the answer is the following. So this class is annihilated by an integer n generically, so over the function field of the coarse moduli space. If and only if the same integer annihilates the co-kernel of this evaluation map up there. And an integer n annihilates the class globally over the whole regularly stable locus if and only if, first of all, this condition is satisfied, and moreover, the integer n also annihilates the mu r's in the center. Yeah, so the quotient of the center modulo its reduced identity component, which consists of all the gm's present. So in this quotient we now only have the mu r's that are in the center, and the condition is that these mu r's are all annihilated by n. So in other words, the r's that appear in the mu r's are all dividing n. So that is the actual result. And how is such a thing proved? On the proof of that, well, this obstruction class is closely related to line bundles on the moduli stack. Yeah, so it will be about line bundles on the moduli stack. So let me say a few words about them, and then I will formulate the relation between line bundles on the stack and the existence of these Poincare families and the order of these Brouwer classes. So if we have a line bundle on the moduli stack, well then, let's look at one point in the moduli stack. So a k-valued point, if you like, is given by a principal G bundle E defined over the curve C. So that's a point in the moduli stack. And since we have a line bundle on that thing here, and we have a point in that thing here, we have a fiber. It has a fiber. LE, which is now just a one-dimensional vector space over the base field K. Since we've taken a K rational point. That's what you have for any line bundle, right? If you pick a point, you get a fiber, which is a one-dimensional vector space. But now you're on the stack. So the stack doesn't just have points, but the points notoriously also always have automorphisms. So this means in this situation, also the you also have an action, just from being a line bundle on the stack, you have an action of the automorphism group of E on this one-dimensional vector space. So that is also part of the datum of a line bundle. So I'll just put L up here. Is an action of the automorphism group scheme, say, on this one-dimensional K vector space. Now that automorphism group is just a multiplicative group. And inside the automorphism group, you have in any case always the center of G. So for every point, you get in particular a character of the center of G. That you get for every point, but I mean the group of characters of the center of G is discrete. And this character will somehow vary algebraically if you vary the point inside the component. So it has to be constant on the whole component, because the component is connected. So what you get is actually one character for every line bundle, and that will define you a group homomorphism from the Picard group of this component in the moduli stack to the group of characters on the center, which is just bookkeeping of the action of these easiest automorphisms that these bundles have. That's a group homomorphism. And this group homomorphism And so this group, together with this group homomorphism, knows everything about all these questions. Yeah? So that is the information that encodes the existence of Poincare families, the order of the obstruction class, and so on. Yeah. Should I try to explain this? Where's the eraser? Ah, there are plenty. Maybe I'll just try to explain the connection in words, since I'm a bit slower than I thought I would be. Oh. Yes. Well, there always is, and that's why I'm making this distinction about terminology, there always is a universal principal G bundle on the product of curve and curve and moduli stack. Now, maybe I'll write a bit also. So, what is the relation between this map and the existence of Poincare family? So, for example, there's the following proposition. There exists a Poincare family for an arbitrarily small for some non-empty open part if and only if this weight map is surjective. That I'll say next. So now I'll explain what the relation is briefly, and then I'll say what we know about this and about that. So what is this relation? Let me say a few words about the proof. Maybe I'll first explain this direction for the case of GLN, because it's a little easier there, and the argument basically generalizes. So assume that the weight map is surjective. For GLN, the center is GM, so the weight is just an integer. Yeah, so surjectivity means that there is a line bundle of weight 1. So assume we have a line bundle of weight 1. So now in any case, there is a universal vector bundle over curve times moduli stack. Yeah. So if you like, if you prefer classical language, the moduli scheme, the coarse moduli scheme, is constructed as a quotient of some quad scheme modulo some PGLN. The moduli stack will then be the stack quotient of that quad scheme modulo GLN, and the universal bundle on the quad scheme will have a GLN action. So it's a GLN equivariant bundle, and hence, by pure formality, it exists on the moduli stack. And that is what always happens. So for purely formal reasons, there is a universal bundle over the moduli stack, but the trouble is it doesn't descend because the center is still acting. Yeah? So on the quad scheme, GLN acts on the universal bundle, but you want an action of PGLN in order to descend it to the coarse moduli scheme. So you have to make GM inside GLN act trivially. And that's what these line bundles do. Yeah, so if you have a line bundle of weight 1, this precisely means it's a GLN equivariant line bundle on the quad scheme, and GM acts with weight 1. So you can tensor with a dual of that. that will cancel the GM action, and now PGLN acts, so the thing descends to the coarse moduli scheme. And that argument can more or less be extended to arbitrary groups. And maybe I'll leave it at that. And not talk about the other direction. Maybe that already indicates that this is related one to the other, because you can use these line bundles to cancel the action of the center on the universal bundle over the moduli stack. And once you've cancelled the action of the center here, it will descend to the coarse moduli scheme.
Where are you pulling that line?
By the second projection. So this is a line bundle on the moduli stack. And, Poincare group of that. And then it's pulled back by the second projection to this product. So that's all I think I said about the proof of that. So actually, as soon as we know what the Poincare group is and what the weight map is, we know all this. That is the moral here. So what is the Poincare group and what is the weight map? That is the second main result here. So there is a lot of literature. There's a substantial literature on the Poincare group of these moduli stacks and also their coarse moduli schemes. So at the moment, let me not put all the names, and we're using that. So I'll mention the earlier results that we are using when I sketch the proof, but the most general result, there I should maybe put one name, which is Telemann, because he has, he kind of had the root system appearing. Yeah? So he proved it topologically for semi-simple groups over the complex numbers, but he also has some kind of this group appearing. That's why I put his name here. That was the first general result, which involved the root system and was for all groups, all semi-simple groups. And we have an algebraic proof for all reductive groups in all characteristics. And it looks as follows. And also we computed the weight map that he apparently was not interested in. We also computed that homomorphism, and I'll describe it in a minute. So here is the Poincare group of the moduli stack. That's the thing we want to understand. Yeah? And it sits inside a canonical exact sequence. So it has pieces which we can understand. There is a canonical exact sequence, and it has the following pieces. So first of all, there's kind of an algebraic part. So even if I would write the Jacobian here, I would have the algebraic part, which is the dual abelian variety, and I would have the Néron-Severi group here. Yeah, that is kind of the model for the statement I'm going to write down here. And the algebraic part is homomorphisms from the fundamental group of G into the Jacobian. Yeah? So this is a finitely generated abelian group. So I can decompose it into cyclic groups, and then I get for each z here, I get the Jacobian, and for each z mod n here, I get the n torsion in the Jacobian. So this somehow just sits inside products of copies of the Jacobian. That is kind of the algebraic part. And then there's kind of a discrete part, which we just call the Néron-Severi group, and which I'll describe further. So that will just be a finitely generated free abelian group, which somehow encodes the combinatorics. And what is that? Well, this has again two pieces. We're dealing with a reductive group. The reductive group is built out of, in some sense, it contains a torus, say its maximal abelian quotient, and a semi-simple group. Right? And Néron-Severi will consist of two pieces, one coming from the torus quotient, and one coming from the kind of semi-simple part. So the part coming from the torus quotient is the following. We can pull back everything we can pull back line bundles, Néron-Severi classes, and so on from the maximal torus quotient, G modulo G prime. So that will certainly appear here, and that is in fact the contribution from the torus part. So it's the Néron-Severi group of the stack of bundles under the torus G modulo G prime. And that Néron-Severi group consists of the Néron-Severi group of the coarse moduli scheme of these torus bundles. Yeah. So this is now just an abelian variety. This is just a product of copies of the Jacobian. Yeah. So this abelian group has a classical Néron-Severi group. And what also is there is a group of characters. There's not enough space. G modulo G of this torus. So that is everything pulled up from the maximal torus quotient of G. That is maybe not so surprising. And on the other side, you have the contribution from the semi-simple part, and that is exactly the group I introduced in the beginning. Yeah. So this group also describes line bundles on the moduli stack up to the algebraic part and things pulled back from torus quotients. So that is that describes the Picard group. Yeah? This describes this canonically, and that describes the Picard group. And now what is the weight map? The weight map is a homomorphism from here, and actually it will depend only on the Néron-Severi class. So the first statement is that the weight map factors through the Néron-Severi group. So all these classes which are kind of algebraically equivalent to 0 have trivial weight. So it will factor here. And in fact, characters of the center also consist of parts pulled back from the torus quotient and some rest, as follows. Well, if you have a character of the maximal abelian quotient of G, which is, by the way, the same thing as a character of G, of course, then you can pull it back. So these two, this torus has the same rank as this group of multiplicative type, and there's a map from there to there, so you can pull back characters. And in fact, the weight here on this part, on the pulled up part, is just the second projection. Yeah? So here what we have is line bundles on the coarse moduli space and their weights. These are the two parts here in the torus case. That is not difficult to see. And the co-kernel here, that describes the weight map on this part, which is not a surprise maybe. And then there is the remaining part. So here, up to characters of the whole group characters on the center give characters of the center of the commutator subgroup. And here the map is precisely up to sign this evaluation map. So from this description of the Picard group and the weight map, the results on Poincare families follow. So now I have 5 minutes to say a few words on the proof of this result about the Picard groups. So one ingredient is to study what happens how does the Picard group behave under central isogenies. So if you have a reductive group G, and you go modulo some finite subgroup of the center of G, so some product of mu r's. If you go modulo that, that's what's called a central isogeny. And this is what the fundamental group parametrizes. So these are kind of coverings in the sense of this fundamental group that I'm using all the time. Then you get an induced map of moduli stacks. So every G bundle, you can extend the structure group to a G mod mu bundle, which means you just go modulo mu in the total space. This will give you a map from the moduli stack of G bundles to the moduli stack of G modulo mu bundles. And if you take the topological type D here, you end up with the image of D in the fundamental group of that, which I denote again by G. So this map you have, and this is actually, this is a torsor under the group stack of principal mu bundles. So, I mean, in very classical terms, if you replace mu, if you take instead of mu, say, GM, if you go from GLN bundles to PGLN bundles, then the map of nice pieces of the coarse moduli space will be a torsor under the Jacobian, and this is kind of the more fancy version of that, and it is true on the nose, on the whole moduli stack. So this is a torsor. So in other words, you can describe line bundles down here by line bundles up here together with appropriate descent data. Ooh, time is almost over. Okay. So you can describe line bundles down here by line bundles up here together with descent data. And these descent data you can understand by pulling back to torus bundles. Yeah, so you pull back to torus bundles on both sides, and you find out that a descent datum for a line bundle up here is the same thing as a descent datum for its restriction to torus bundles. So it will descend if and only if its restriction to torus bundles descends. And on torus bundles you understand everything. So this combinatorially. So this allows you to descend once you know what happens after restricting to torus bundle. Yeah. So you can go from a group to a cover. This more or less, with some extra work, allows you to go to simply connected groups. Yeah, more or less, you have to, what remains to do is to answer the question for simply connected groups and to understand what happens if you pull back to torus bundles. And for simply connected groups, that's the case where there's a lot of literature, which has been studied most. In particular, There's work of Christoph Sorger in characteristic 0 and Faltings in positive characteristic, which prove that the fundamental group, the Poincare group is just set in the in the almost simple case, simply connected almost simple case, which means if we have several factors, then it is one copy of Z for every simple factor, and that is also exactly what this combinatorial group was in the simply connected case here. Yeah. So from work of Sorger and Faltings you get that, and that description, although it is now this isomorphism is given now rather artificially, both are one copy of Z for each simple factor. This isomorphism that you get that way is functorial in G. Yeah? That is due to Kumar-Narasimhan Ramanathan, who observed that who found out that if you pull back line bundles along a homomorphism of simply connected groups, the Poincare groups are Z, so you get a multiplication by an integer, and this integer is the Dynkin index of this group homomorphism, which is by definition the number with which these generators are multiplied by pullback. Yeah? So you get this functorial isomorphism, and now it remains to understand in the simply connected case, and it remains to understand what happens if you pull back to a torus bundle. Yeah? So and pull back to a torus bundle that you can now, due to functoriality, just compute for SLN, and what you get for SLN includes this map, more or less, and you get some formula from which you can then deduce what happens there. So time is up. I think I should stop now here. And these are some of the, I hope I give you some impression of the ingredients that go into there. Thank you for your attention.
Any questions?
Yeah.
You say there exists some open set, and the case which you showed, of course, produced everything as the open set. Sometimes you mention regular as the open set. But what open sets come up when you say there exists an open set?
Okay, yeah, there are a few more subtleties which I put under the rug here. If the center is GM, if the center is a torus, then you can run the same argument and you'll automatically get it on the regularly stable locus. But if the center is, for example, mu r, then in order to descend the universal bundle, you need a mu r bundle on the stack. But what you have by assumption is only a line bundle whose weight has order r. Yeah, so you have a line bundle whose rth tensor power has trivial weight. Hence, this power will descend to the coarse moduli scheme. Hence, there it will be Zariski locally trivial. There you can choose a trivialization. On that open part, the bundle of on the stack is a mu r bundle. And that mu r bundle you can use to descend. So you don't really know which open parts you get.
Any more questions? In that case, very thanks, Victor.